We spent the last week studying how mammals thermoregulate their bodies. Thermoregulation is important to animals because many of their bodies' biochemical processes would stop working if their temperature strayed outside the normal range. Thermoregulation of the Earth is important for a similar reason. The balance of inputs and outputs of heat to the Earth maintain the climate that we're used to. In order to understand this balance, we have to figure out what are the processes that give or take away thermal energy from the Earth system. Of course, the only major source of heat from outside the Earth is the Sun. Each second, it produces about 382 septillion joules of electromagnetic energy. Luckily for us, not all that is directed towards the Earth. The part that is travels 149 million kilometers in a little over 8 minutes, traveling, of course, at the speed of light. So what's the intensity of the light that actually hits the Earth? In other words, how much energy hits each square meter of the Earth's surface? In order to figure this out, we need to look at how the energy spreads out as it leaves the Sun. The energy that's emitted in 1 second by the Sun spreads out spherically in all directions. You can think of those 382 septillion joules spread out over the surface of this sphere, drawn here in 2 dimensions, of course. As the light energy moves further and further from the Sun, the sphere that the energy is spread out over gets bigger and bigger. As it does, the energy is spread out over a larger and larger area, meaning that the intensity, or power per square meter, gets smaller. We can calculate this intensity by just dividing the power output of the Sun by the surface area of the sphere at the distance from the Sun that you're interested in. Because this is a sphere, the surface area is 4 pi times the radius squared. Interestingly, the intensity that reaches the Earth is not constant over the year. That's due mostly to the fact that the Earth's orbit around the Sun is not perfectly circular. The orbit's elliptical shape means that the Earth will be further from the Sun at some times during the year, and at those times we'll get less energy each second. It turns out, though, that the change in distance isn't all that great, and there's just a 6% difference between the most and least power that hits the Earth over the course of a year. Also interesting is the fact that we're actually closest to the Sun during our Northern Hemisphere winter, the coldest time of our year. So that raises the question, what causes the seasons? Since it's obviously not tied to how far we are from the Sun. Here we have a diagram of the sunlight hitting the Earth at different latitudes. As you can see, the sunlight coming in actually spreads over different amounts of the Earth, depending on where it hits. Let's compare how much sunlight a person gets at different latitudes. Each of our persons is standing on a square meter of land. The important difference between them is the orientation of the square meter towards the Sun. Let's find out why that matters. The orientation of our square meter matters because at different angles towards the Sun, it will receive more or less sunlight. The more parallel to the Sun's rays it is, the smaller the cross-section it presents to the Sun, and the less energy it receives. Conversely, the more perpendicular to the Sun it is, the more energy it receives. On the Earth, this means that a person on that square meter at the equator will receive the maximum possible energy per second from the Sun, because his spot is perpendicular to the direction that the sunlight is coming from. As you move towards the poles in latitude, each square meter receives less and less. The North Pole receives no direct energy in this configuration because it is perpendicular to the Sun's rays. What this means is that each of our persons will receive a different amount of heat input from the Sun depending on how perpendicular or parallel they are to the sun's rays. Let's figure out how to calculate the amount of heat that hits a square meter of the Earth each second, the rate of heat input. The maximum value for this is 1360 watts per square meter, which is the value at the spot on the Earth directly perpendicular to the sun's rays. In this diagram, that's at the equator. This value is the average value over the year and is called the solar constant, which is slightly ironic because, as we've seen, it varies some over the year. Let's figure out how to find out what the amount is in other places, such as where we are in Myrtle Beach. Now, Myrtle Beach is located at approximately 33 degrees north latitude. But what does that mean? Latitude is defined with a line from the center of the Earth to a location. The angle between that line and the equator is your latitude. Of course, this means that the equator itself is 0 degrees latitude and that the poles are 90 and negative 90 degrees. We can then write the effective solar heat input rate as a solar constant times the cosine of the latitude. The effective solar heat input rate is the rate at a certain latitude. This works because the cosine varies from a value of 1 at the equator to a value of 0 at the poles, making our rate 1360 watts per square meter at the equator and slowly reducing to 0 at the poles. So we've determined how the rate of solar heat input varies by latitude, but how does that help explain the phenomena of seasons? Well, in order to explain that, we need one more piece of information about the Earth's orbit around the Sun. Coming back to our diagram of the Earth's orbit, we see that the line through the equator is not always pointed directly at the Sun, which was one of our assumptions in the previous calculation. The Earth's axis is actually tilted at an angle of 23.5 degrees. This means that on one side of the orbit, illustrated here on the left, the equator is actually 23.5 degrees below the line directly to the Sun, and on the opposite side of the orbit, here on the right, the equator is 23.5 degrees above the direct line to the Sun. When the Earth is halfway between those points, the tilt is sideways relative to the Sun, and the equator does point directly at the Sun. These two extremes are known as solstices. Civilizations have celebrated them for millennia as important celestial events. On the day when the equator is 23.5 degrees below the line towards the Sun, usually around June 21st, the Sun rises at its most northerly point, directly above 23.5 degrees north latitude. On that day, called the summer solstice in the northern hemisphere, that location north of the equator is actually the spot perpendicular to the Sun's rays and receives the most heat per square meter. On the northern hemisphere's winter solstice, usually around December 21st, the latitude on the Earth that is 23.5 degrees south of the equator is oriented perpendicular to the Sun's rays, and it receives the most heat per square meter. As you might expect, on the days that we call the spring and fall equinoxes, since the line through the equator points directly at the Sun, on these dates the equator really does get the most heat per square meter, as we previously described. So how can we use this to determine the rate of heat inputs to a particular location if its orientation relative to the Sun changes over the course of the year? Well, we can figure this out for the solstices using geometry. On our summer solstice, Myrtle Beach is still 33 degrees north of the equator. However, since the equator is now 23.5 degrees below the line to the Sun, the angle between our latitude and the direct line to the Sun is only 9.5 degrees. We call this angle the effective latitude, and we use this in our previous equation to determine the rate of heat input per square meter on that day for our latitude. Similarly, on our winter solstice, Myrtle Beach is still at the same angle relative to the equator, but since the equator is now oriented 23.5 degrees above the line towards the Sun, the effective latitude for Myrtle Beach is now 56.5 degrees. This means we're receiving much less heat per square meter on that day than in the summer. Putting all this together gives us a physical reason for why we receive more heat in the summer than in the winter. In the summer, the tilt of the Earth makes our spot on the Earth more perpendicular to the rays of the sun, and so we get a higher rate of heat input per square meter in the summer months. In the winter, the opposite is true. We are tilted at a very large angle from the sun, and that makes the rate of heat input per square meter much smaller. So, when you come to class, you should be able to explain why the heat rate input per square meter depends on the latitude, explain why the effective latitude changes over the course of the year, and calculate the rate of heat input per square meter given the solar constant and the effective latitude.